The purpose of this show is to explore continuity conditions, which will play a tremendously important role in solving more complicated problems. So I'll be working with the fourth order differential equation, and I would like to analyze this very basic looking problem. So I have a simply supported beam loaded by a force P. So I can write down boundary conditions at x equal to 0, v is equal to 0, and m is equal to 0, which implies that v and the second derivative are equal to 0, and the same story at x equal to L. V and m equal to 0 implies that v and v double prime equal to 0. I can also naively claim that in this problem q is equal to 0, and then this becomes the differential equation with 0q and these boundary conditions. And it is very easy to check that v equal to 0 satisfies the differential equation and satisfies all boundary conditions. But this is absurd because obviously there will be a deflection line under the force. It is also somewhat absurd that in this problem we don't have P showing up anywhere. If we don't use P, it means we don't use the essential piece of information about this problem. So to sort out difficulties, let us go back to the problem and say, let us try to construct two solutions. The left branch between 0 and L. For this branch, the differential equation is fourth derivative equal to 0, and I show the left branch with the minus. I can also impose two boundary conditions at this point, v of 0 and v double prime of 0 equal to 0. I can do a similar thing for the right branch. X is between L and 2L. Again, I have the same differential equation and the same boundary conditions. Now, it's all good. I can just simply copy what I had from the previous page, and now I can make some observations. There are 4 boundary conditions in total, 2 per point. This is the left support, this is the right support. However, each branch of the solution involves 4 constants, 4 here and 4 here, so that the total count of constants is 8. So clearly there is a deficit. This deficit is resolved by imposing continuity conditions at x equal to L, and they will involve relationships among v minus and its derivative and v plus and its derivative. So to derive those 4 relationships, and that's exactly what we need, let's look at first geometric continuity condition. So at x equal L, so everything is done in the midpoint. V minus must be equal to V plus. If it's not the case, it means the beam is broken. We also claim that the slope or the derivative is continuous, meaning V prime minus is equal to V plus prime. What does it mean? It's good to look what happens if this condition does not hold. Think about your arm and the elbow. So the elbow is a hinge, and if you look at the elbow, V prime minus is not equal to V prime plus, because the upper and lower arm can bend at different angles, right? So, but for your upper arm, this condition holds unless, God forbid, you have an open broken bone, right? So we don't want to look at those. Static continuity, still x equal to L. And now I show a free body diagram for a small element delta x centered at the midpoint. Actually, this free body diagram was used in the past when we talked about shear force and bending moment diagram and were concerned with the jump conditions. So let us explore this. So the equilibrium equation for this element for the forces V minus, V plus, and P, and I'll calculate some of the moments about this point. So involves two couples, and each force has the arm of delta x over 2. And now if I simplify these equations, I will conclude that V plus minus V minus is equal to minus P. What does it mean? It means that if I come from here, from a little bit to the left of the midpoint where the force is V minus, and transition to a little bit to the right of the midpoint, the shear forces will jump abruptly, and the jump is minus P. That's the rule we know pretty well from constructing the shear force diagram. Now, if I look at the moment equilibrium equation and set delta x to be small, I conclude that m plus is equal to m minus, which I can say is that the moment is continuous at this point, or I can say that the jump in the bending moment diagram is equal to 0. Equipped with that, we can summarize the continuity conditions. The deflections and the slopes are continuous, so is the moment, but the shear force experiences a jump minus P. Now I can rewrite these physical continuity conditions in terms of mathematical continuity conditions, where theta is replaced with V, m replaced with minus EI V double prime, and capital V is replaced with minus EI V triple prime. Okay, so now we can view these conditions as the complementary conditions to the boundary conditions that will allow us to determine all 8 constants. So how it's done? So I start with the left branch, 0 here, then I integrate 4 times. And that's what I obtain at the end of the integration process. A cubic polynomial, and of course the fourth derivative of the cubic polynomial is 0, and that's pretty obvious. Pretty much the same happens with the right branch, except that now I call the constants D rather than C. So here I have 4 C's, here I have 4 D's. Once I determine the C's and the D's, I have everything I need. So the boundary conditions, these are my equations for the boundary conditions. These are my equations for the continuity conditions. And now I just simply substitute cubic polynomials for V and V plus into these 8 conditions, evaluate them. These guys at 0, these at 2L, these are all evaluated at L. So I end up with 8 algebraic equations, and I can solve them. Obviously tedious. Obviously, I'm not going to go through the details of solving a system of 8 equations with 8 unknowns. The bottom line, it can be done. And here are the constants. Now, I can take this constant and substitute it back into V minus and V plus, and I obtain 2 expressions. So on the left segment of the beam, between 0 and L, that's the expression for the deflection. On the right segment, between L and 2L, that's the expression. I can also evaluate both expressions at x equal to L. A, I will find that V minus and V plus are equal, and B, I'll find that they're both equal to PL squared over 6CI, which is the maximum deflection of the beam, or the deflection under the force in the middle.